Okay, so it's my great pleasure to present this to the OSG community. This is Chi-kwan Chan from the University of Arizona. I'm representing the Event Horizon Telescope collaboration to tell you how we use the OSG and simulation to turn our black hole image into science. So, all right. I guess the best way to get started is to show you this movie. It really helps us explain what we are doing in our project. So this is a optical image of the Milky Way. I guess if people look up in the night sky, especially during summer or winter time, you can see part of this is the Milky Way. I hope many of you will recognize this. Now, if we use a longer wavelength, shorter frequency to observe the same sky, then this is what we will see. Okay, and we can zoom into the central part of the Milky Way. You can see it's pretty bright with a lot of interesting features. But for this talk, we were not interested in these features. We will just keep zooming in. This is what we call the mini spiral. And then there's still a bright point in the middle, and we keep zooming in. And this turns out to be a supermassive black hole at the center of the Milky Way. So this picture here is observed by the Event Horizon Telescope collaboration. And this picture is part of the team who make this image possible. So I hope this movie gives you an idea of what we are doing. We are trying to create the highest resolution image of black hole possible. So why are we interested in doing this? The main reason is we want to test Einstein's theory of general relativity. This talk is not meant to be technical, so I will just go through this very quickly. On the left-hand side of the Einstein equation, this is the space-time curvature, pretty much. And on the right is the energy distribution. So Einstein's general theory of relativity pretty much says that the space-time tells matter how to move and matter tells space-time how to curve. And this is the thing that we want to test. All right, so you're assuming you're in space far away from any heavy object, then the space-time is flat, and then particles, photons, when they move through this flat space-time, they will just go in straight line. But now when a heavy object presents, it will curve the space-time. And now the particles and photons, although they still want to move in the most strict path possible in the four-dimensional space-time, the projection to 3D will appear that the particle actually curve around the heavy object. And when the object is so heavy and so dense, not even light can escape this surrounding, and then we have a black hole. So black holes start as a theoretical prediction. So about 40 years ago, people got this thought experiment that if we shine a flashlight to a black hole, because of the curved space-time, some of the light will actually turn around the black hole and then go back to us. So this gives us the black hole glory on the left of this image. It's a very old paper, more than 40 years ago. And more recently, we can do numerical simulation. We can do your calculation. The assumption changed a little bit because we don't have flashlight in space, right? So the current models that we put emitting plasma around black hole. And then we, after we do the calculation, we still see very similar feature, a very bright ring around the black hole. And this is the thing that we want to observe with the Event Horizon Telescope. So, in order to make a theoretical prediction of black holes, there are multiple steps. So for the first steps, we need to follow this plasma around the black hole. We use an algorithm called general relativistic magnetohydrodynamic simulation. That's very difficult to say, but it pretty much just describe how plasma interact with magnetic field around black hole in a curved space-time. Once we do this calculation on HPC resource, we have a description of how the plasma and magnetic field look like around black hole. And once we do this, we can do the second step to create an image. The image is done by general relativistic ray tracing algorithm. The idea is we set up a virtual screen, and then for each pixel of the screen, we just follow them backward to the emitting region. So as what you represent on this infographics, you can see on top right, that is the simulated image that we are computing. And we will compare this type of simulation with the observation in order to understand the space-time property, the plasma property around the black hole. Now, so after we do this, GL MHD, GL ray tracing calculation, this is what a typical movie will look like. So in the middle, we have this ring region that I brought up earlier, and then we also have this funnel region. The funnel is a region with very strong magnetic field. You actually push out plasma from the black hole and create very, very large scale jet. The jets can be larger than the whole galaxy of the black hole. And around the equatorial region, you can see the accretion disk, and you can also see this very interesting lensing effect around the black hole. So it's interesting to make the connection with an earlier talk that you hear about using machine learning to search for strong gravitational lensing signature for cosmology. So in this sense, the photon ring that the EHT is observing is an extreme version of that. The black hole is so dense that it is curving and creating lensing effect of the plasma around it. So this is, again, the thing that science that we are after. So if we survey the whole sky and we look at the brightest object and the largest object on the sky, there are actually only two objects that we can resolve their event horizon. But even though these are already the biggest object, biggest black hole we can find, they are still tiny. They are so tiny that they are just like putting a donut on the surface of the moon. So the diameter is what we call 15 microarcsecond. That is very, very small. Now, however, I actually don't know how far away is the moon. So I guess this picture here is probably not too useful for many of us. So another way to say it is we want to zoom in to the tip of a pencil located in Tucson from Wisconsin. This is how small of a black hole that we want to resolve. And conventional telescope actually wouldn't work because of physics, because of the limitation of optics. There's no way we can resolve such a small object. So in order to overcome this, we use a technology called very long baseline interferometry. So the idea is we use multiple radio telescopes on the Earth. Each radio telescope, you can think about it as a single pixel antenna, just like a TV antenna, that are sensitive to a particular region of the sky. So in this graph here, this is the dot circle on the top right. So using a single radio telescope, you will be sensitive to the circle, but then you wouldn't be able to resolve features inside it. But with multiple telescopes, something interesting will happen. So imagine in this sensitive region, you have one bright feature coming up, sending radio wave to Earth. This radio wave will arrive to the Earth to multiple telescopes, two telescopes for this example. And in this drawing, the wavefront from the black hole arrive at the telescope at the same time. So we know there's emission from this region. Now imagine there's another bright feature in the same area. With a single telescope, you will not be able to distinguish these two features. But with multiple telescopes, if we look at the blue wave here, because of the angle, the small angle difference, the wave actually arrived to one of the telescopes slightly earlier than the other. And by measuring this time difference between different waves, we are able to distinguish different sub-features in this region on the sky. And this is exactly what we do in the Event Horizon Telescope. So this is a little bit of math, but don't worry too much about it. So in 2017, we used 8 telescopes all around the world to form the EHT array. So all the results I'm going to present today come from these 8 telescopes. But of course, the EHT is an experiment, and we just constantly upgrade our telescope. So in 2018 and later, we have 3 more telescopes as we show in this picture. And this is a picture of all the data we gathered recently in the 2022 observation. So we actually record this radio waveform from black hole to this hard disk module. And all these hard disks on this table contain 4 petabytes of data took in 2022. For our 2017 observation, the whole experiment took about 5 petabytes of data. So you can tell your technology really advanced. We increase our bandwidth. We have more data, high sensitivity these days. Now, although we have multi-petabyte of data, it turns out when we want to reconstruct the black hole image from this interferometry data, the solutions are not unique. There are actually infinitely many possible images that are consistent with data. So, such as the image shown in this movie here. So the way we handle this is of course, the simple way is then you just average all of this possible reconstruction and then conclude that we have a picture of the black hole. But this is not quite enough because we do want to pull out some science from the observation. So the way we handle it is we use machine learning, just very simple clustering algorithm to classify the black hole image into 4 major categories. And it turns out most of these images still show a ring with a very few exception. So using this, we can put statistics and error bar on the image and then conclude that, yes, we do observe the photon ring at the center of the Milky Way. All right, so far so good. So we have your very nice black hole image, but you may ask, so what? Why do you spend so much time just to take a picture? So the next step of the experiment is to turn the image into science. And this infographic I showed you earlier is very important because the technique we are using is just forward modeling. The idea is we make some assumption. We do these GL-MHD simulations. We have the plasma model, and then we assume certain plasma and black hole parameter. We assume some black hole spin, some plasma temperature, and then we simulate many black hole image, and then we compare all of these image with the observation to pin down what type of parameters are consistent with the observation. So as you can imagine, this is a very big computation task. So without the OSG, we will not be able to finish this. So so this is just a snapshot of the multiple software that we put on the OSG. Because this is not a technical talk, so I actually didn't prepare for the technical details. But roughly speaking, we stage our simulation data on OSG data storage, and then we just package our software using Condor. So here we have the IPO software. That is the main software that turns the simulations into image. And then we also have another software called GL Monty that does Monte Carlo radiative transfer around black hole. So what that does is it also take into additional physics such as inverse Compton to give us the whole spectral energy distribution. So this is very important when we need to compare the simulation with, for example, NASA observation from Space Telescope. And then we also have a simple pipeline that is synthetic data generation. So I saw Matt is on the call, so I want to shout out to him. He's very helpful to help us put the Pegasus pipeline together for the synthetic data generation. So with all of this, software and pipeline ready, I think in 2021 we actually did our production run. So for a few days, we were actually the top user of the OS pool. And you can see the Twitter post by Fabriel Ocel that we are doing a lot of data crunching on the OSG. So after this production one, we had the biggest black hole simulation library today, and this is a whistle of the simulation library. So for each parameter set, we do have movies of the black hole that is varying and changing, but just a single movie is not enough. So we change the inclination, the viewing angle of the black hole, and you can see with different viewing angle, the black hole look actually different. But that's not enough, so we allow the black hole spin to change as well. So for this, it's not just the shape of the black hole image, but also the variability and other property. And in addition to that, we also changed the electron temperature. The electron temperature turns out to be a free parameter. And then we also allow us to change the magnetic field configuration. So on the top half panel, all of those magnetical dominate accretion flow. So the magnetic field around the black hole is so strong to stop the plasma falling in. And in the lower half of the movie, those are the standard turbulent accretion flow. So just looking at the movie, you can already tell there's some difference between different physics, different assumptions. So the next thing we did was to compare the simulation library created by the OSG with real observation data. So if we compare the library with only the EHT results, so wait a second. So if we compare it with the black hole size from the EHT, we rule out a little bit of the black hole. But if we compare it with the shape, we actually rule out many possibilities. And we compare with the spectrum. So this is the GR1T calculation. We rule more. And then with low frequency image size, we rule out even more. So at the end, with this very big simulation library generated by the OSG, only 2 models survive after we compare with our observation. And this is one of the best models we have for the supermassive black hole at the center of the Milky Way. This is a phase-on model. So to me, that is a little bit surprising. This is a 2-temperature model. So we know now the electron temperature at the center of the Milky Way is lower than the ion temperature. And then the spin is 0.9, but the spin is very hard to measure, so don't trust that too much. Now, together with our recent result at the center of the Milky Way and our early result for the M87, by combining these 2 results, we can actually tell that Einstein's prediction is correct across 3 orders of magnitude for supermassive black hole. And now if you combine this result together with the gravitational wave detection from LIGO, we conclude Einstein is right across 8 orders of magnitude in black hole mass. So this is a pretty remarkable constraint. So with all of this, this is my summary slides. The EHT captured the first horizon scale image of the supermassive black hole at the center of M87 and Sagittarius A star. So with OSG and black hole simulations that I show you, we actually decode this hidden information in the image and learn that the supermassive black hole at the center of Milky Way is likely to be 2-temperature, is pole-gray, meaning that the accretion flow is spinning in the same direction as the black hole spin, is magnetically dominant, and to my surprise, it is phase-on. So up to this point, we show that Sag is consistent with a curved black hole. So Einstein is right again, even in extreme gravity. Something I didn't mention earlier is thanks for the simulation library, we can actually compare not just the average image, but also the detailed variability in the simulation observation. We actually see that the observation is less variable than what we expected than the simulations. So this is a surprise to many of the black hole theorists. So on one hand, this is very good for image reconstruction because it's less variable. But on the other hand, this may indicate that new physics that we haven't taken into account in our modeling. So I guess right now we have a very successful collaboration with the OSG that create all the scientific results I showed you, but we are still collaborating. So I want to highlight two of those. One is we want to expand the OSG use case to also include the observation data. so that the EHT can turn around our your observation result faster. So this is done with the path team. So I want to shout out to Christina, Rachel, and Brian to helping us on this. And then the other thing is all the simulation reconstruction that I showed you earlier is only done by a few people in the EHT. Partly because many of the people in the collaborations are observers and they are not very comfortable in writing their own script. So with that, we are collaborating with Rob Quick to develop a science gateway to send jobs from a graphical interface to the OSG. So Rob is going to present tomorrow 1:30. So I encourage you to listen to his talk. So that's all I have for today, and I welcome question. Thank you very much.